We've already seen what the sample distribution looks like if I pull from a population that is normally distributed. What would happen if I pull samples from a population that's not normal, or in this particular case, skewed? So we're going to look at a simulation regarding skewed distributions. And what we have here is a population which is skewed right, which we can see here. The mean of this skewed population distribution is 14, and the standard deviation of the population is 11.8. So let's say, for example, I want to have a sample size of, I don't know, 3. And I'm going to repeat that process, sampling and pulling from this skewed population here 1,000 different times. And each time I pull, I have a sample size of 3. When I do that, here at the bottom, you can see the results from all 1,000 of my samples that I pulled. And you'll notice that if we want to start with just the shape, what does the shape of this green histogram look like? Well, the green histogram is kind of exhibiting a skewed right distribution, similar to the population's distribution we see up here. The center of my sample distributions is 14, which is pretty close to the center of the population's distribution. And then you'll notice that the standard deviation of these samples is less than the standard deviation of our population. So that's consistent with what we've seen before. The problem we have is that the sample distribution is exhibiting a skewed shape, and we want it to be more normal. How about we increase our sample size to maybe 10? So if I increase this sample size to 10 and we go back and we repeat our process of repeating the process 1,000 times, now you'll notice that the distribution or the shape, right, of all of the sample means that we took, all 1,000 of my sample means, this looks pretty darn normal. This has moved into a normal shape here, which is what we want to have. And notice that the center of our sample distribution is pretty close, again, to the center of the population's distribution. The standard deviation of the sample's distribution is much less than the standard deviation of our population's distribution. So again, the mean and the standard deviation are following that same process or rules that we saw previously on normal distribution populations, but we had to increase the size of our sample to get the shape of our sample distributions, or sample means, I should say, to get the shape of our sample mean histogram to become more normal. In fact, if I were to change my sample size to, I don't know, let's change it to 25 and just see what impact that has on our 1,000 samples, you'll notice here that we've got a really good looking normal shape for all of those sample means. Remember, this is the histogram for all 1,000 different sample means that we are pulling from a population's distribution, which was skewed. And again, you can look at the mean, the standard deviation of our population compared with the mean and the standard deviation of the sample means, and they are following the same rules that we saw previous. So what does that mean for us? What this is telling us is when we have a population that is not normal and we want to collect over a long period of time, if I were to collect the sample, if I was to find the sample mean from a sample that came from a non-normal population, the larger the sample size, the more normal my distribution becomes. And it really kind of depends on how skewed your population data is as to how quickly your sample means are going to start to move into that normal shape. So just like we saw a moment ago in our simulation, here we're looking at a skewed distribution from the population. And when my sample size is relatively small at only a size 3, the sample distributions, or the sample mean distributions, are still somewhat skewed. And you can see that as we increase that sample size from 12 all the way up to a sample size of 20, the sample mean from each one of these samples we're pulling from end up taking the shape in the long run of a normal curve, which is what we want. We cannot apply a normal model to a skewed or non-normal population without doing something, I should say, we can say to that. So this brings us to this rule here, and this rule that we are going to identify is called the central limit theorem. So in gray here, I have in our screen, if the distribution of your population is unknown, so if you don't know what it is and it's not explicitly stated in your context, or if your population is not normal, then the distribution of your sample means become approximately normal as you increase your sample size, which is what we saw above here when we went from a sample size of 3 to 12 to 20. Our sample mean distribution became normal as we were increasing the size of our sample. So we've come up with kind of a consensus for a number, and the sample size we're going to try to shoot for is a sample of size of greater than or equal to 30. As long as your sample size is greater than or equal to 30, you have met, let's say, the requirements of your central limit theorem. So again, this has to do with the fact that if, number one, I don't know what the shape of my population is, or if the population is skewed, as long as the sample size of your sample is greater than or equal to 30, you will have a sample distribution that behaves in a normal way, and we can therefore apply the normal model.